How sometimes it can seem like, oh no, there's lots of equations. So we have the, started with momentum, being mass times velocity, inertia and motion. So learning that it's not just inertia, but how fast you go matters as well. And then if you're going to change that, in order to do so, just like before, when we wanted to change something's motion, it's happy with its state of motion, whether that be at rest or moving. The only way to change it is to apply a force and cause it to change its motion, thus its velocity, which means it accelerates. You apply a force. So likewise, if you change momentum, you apply a force, obviously for a certain amount of time, because you can't do it instantaneously, and you get a change in momentum. We call that impulse. So now we see how the time matters with force. If you take longer to do something, you don't have to apply as much force to bring about the same change. Change in what? Change in momentum. Likewise, you apply that force, it's still for the same amount of time. It's going to cause a change in momentum. But if you displace something and move it, then you've done work on that object. Or some objects can do work on other things. And that transfers the energy. We have the work energy theorem. That amount of energy done by this force will cause a change. And energy, total energy is always conserved, but it can change forms. And our two types in Chapter 7 are kinetic energy, which is the energy associated with motion. Emphasize the squared term there, because momentum is direct. But that one's squared. And then potential energy, an energy associated with motion, position. It can be stored somehow in something by how it moves. That one, gravitational potential energy, is based on its height above a certain substance, the table or the ground or whatever. And it can convert back and forth. Or it can leave both of these and turn into some other form, such as we saw last time, heat. I told you was a form of energy. The frictional force acts on things over a certain distance. So friction can do work on the object and change its kinetic energy and convert it to heat. Anyway, there's a little review. Questions? Did it work, TLT? They're still working on it. Oh, that's good. Always good to just restart, right? So, I wanted to share two things I found in the world around me. It had to do with physics, because they're right on our topics here, mostly with the momentum and impulse. One, where'd it go? Here it is, right in front of me. Read an article, and before this class, there's a professor who's also a medical doctor. He teaches the physics of the human body. And so I do lots of demonstrations for him. And he recently has finished the unit on bones and fractures and injuries. And I read this little blurb about bone, but specifically with the femur, how there's a trabecular bone. It's kind of spongy. It's got more air pockets. Who's familiar with this? Anybody in biology know more about this than I do? Trabecular bone. Where's that at on the femur? On the ends, yeah. Let's see. Forgive my drawing, but let's see. You got the part that goes into the hip socket, right? And then, whoop. I don't know. Something like that. Down here and whatever the other end looks like. And yeah, it's more up here. It's spongy. Trabecular bone. And then the other kind is called, what's it called? So the spongy bone and hard bone, it's called cortical bone. And, well, it's more dense. It's harder. So basically the idea here is you got hard bone, and that's around the outsides mostly, and more in here. But there's some spongy trabecular bone on the ends. How would that help? What do you think? What's that? Oh, I thought I heard something. Think in terms of momentum and impulse. That's your clue. What do we like to wear so we don't get injured? helmets, pads. Yeah, we have airbags in cars because they do what? Yeah, they're going to increase the distance it takes to stop you, which will take more time. If you increase the distance or the time, then you don't need as much force to have that same change in energy or change in momentum. But the point is, yeah, you increase that distance or time, you don't need as much force. And the femur being the biggest bone, when you do this, it's getting jammed and compressed by your big hip and everything. And you don't want it to break. So, don't know if it was planned or not, but it works. This spongy bone can give a little more to extend that distance in time. And thus, it helps the force of impact on your femur to be less. And it's less likely to break. As if this whole thing was cortical bone, hard bone, solid and perfectly rigid, it might be more likely to break, depending on the material it was made out of. If it was all cortical bone, it would break easier than if it had that spongy bone. I thought that was interesting. I didn't ever realize that before. So you can use impulse in the human body. Second, I had the opportunity to listen to Mark Kelly. He's an astronaut. He's retired now, but he's a twin. And his twin brother, Scott Kelly, is currently up on the International Space Station for a year. He's been up there 11 months. He comes home next month. It'll be 12 months. He holds the record for the longest time out in space for any American. And they just want to see the effects that's going to work. And since he has a twin, he goes around, doing socializing. But they're both astronauts. They both spent time up there. But his brother's up there right now. So yesterday, Mark was explaining a few things, some question and answer period, and the engines. The space shuttle program ended. They're trying to do with SpaceX and other things how to get up there. But how do we get payloads up? And there's kind of a debate on which way to go. Chemical rockets, kind of like our alcohol rocket that we had, where you just basically burn fuel and throw it out the back. Action, reaction. If it pushes on the gas, then the gas can propel it. And presently that's what we've been using. Burn a lot of force for a short amount of time. Maybe burn it for 15 minutes. And that's a plan. That's still on the books for maybe how we could get someone to Mars. Just burn a lot for a short amount of time, get up to speed, escape our gravity, get on our trajectory to Mars, and then it's not like you run out of fuel, but you turn it off, and what keeps you going to Mars? Inertia. And that would work. It would take probably 6 months to get there. Well, they're looking at ion plasma engines, he said. He's like, he would prefer that. And they don't provide as much force. They're throwing less massive stuff out. But they can, if you throw it out fast enough, you can give a lot of momentum. And if you change that momentum, you're still applying an impulse. And you need a certain impulse to escape Earth's gravity, period. But if you can do it for a longer amount of time, you don't need as much force. And maybe you don't run out of fuel. So this ion plasma they could keep doing for much longer. Probably like for half the trip. Turn it on, get going faster and faster and faster. And then turn it off or turn around and start thrusting the other way to decelerate. And I think maybe you can get there in 3 months. But I like this whole interplay with impulse, change in momentum. Current rockets, a lot of force, short amount of time. Let's get us out and just coast the rest of the way. Well, you can make a different engine where you can burn for longer. You don't need as much force and still have the same effect, or maybe even better, depending. Anyway, I thought some of you would like that. I found it interesting. Any of you notice anything in the world around you? That's all right. Give you the chance. All right, let's tell you one more thing. here, and that is power. So work says nothing about how long it takes to do work. We got the time down here in impulse and change of momentum. Work just matters for distance. So if I'm going to exert a force on myself to overcome my weight, that's the force I need to push up, right? And I just raised myself up to here, force over distance, I did work. How does the work I do compare if I do it like this? You sure? Sure it's the same? Who thinks it's different? A few of you. Why do you think it's different? That's what we say. I'm working harder. And who believes that I'm actually working harder to do this? I believe that one. I can feel it. You know, if I were to go run up and down these steps, I'd start sweating. But if I just walk up and down, so yeah, you physically work harder. We say that. We work harder. The difference is the time factor. And that's where this other term in Chapter 7 comes in, about power. Power. And that is a big P. So I don't know how you want to distinguish that from momentum. That is generically energy over time. So in our case here, work over time. So what in science, I'm doing the exact same work. You were correct. Is it Casey? You're correct. It's the same amount of work. Because it's the same force whether I go like this, and I move the same distance. And that's all work says. Force times distance. But if I do it more quickly, in less time, power, I'm exerting more power. And that's the rate at which I'm using energy, or transferring my energy. Does that make sense? You've heard of the term power before. You pay the power company, right? Because it's the rate at which you're using the energy. You're not just paying for the energy. It's, well, how fast are you using it up? You go back in the back and look at your electric meter spinning. Well, they're digital now, but they used to have that wheel. And the faster it was spinning, you knew the faster you were using up the energy. You could be using the same amount of energy, but more power because you were using it faster. So there's two ways to look at this. Well, let me say the units first. Go back and get units. Momentum, you've probably realized, doesn't have any funky or common unit. And several weeks ago, how would you figure out the units of momentum? Well, what's the units of mass? Kilogram. And the unit for velocity? Meters per second. So that's the unit for the SI, standard unit for momentum. Kilogram, meter per second. And it doesn't have a fancy name like Newton did, you know. Let's look at energy. If we take work, let's see, force is in newtons, and distance is in meters. So a Newton meter is a unit for energy. Now that's common enough that they define that as a joule. It's called a joule. In America, probably more common. There's many units for energy, and most common is probably the calorie. When you look at your food, calorie is another unit for energy. It can be converted back and forth between joules. In science, we use joules. Let's look at these two, though. Guess I ran out of room here. Kinetic energy, 1/2 mv squared, so that translates to mass is kilograms, and velocity squared. Meters per second, but it's squared. So a kilogram, meter squared, second squared. That actually is, if you figure this back out, the same thing as a Newton meter, which is the same thing as a joule. And potential energy, I bet you can see where this is going. Mass is in kilograms. I'm blocking now. Acceleration is meters per second squared times another meter. So you can see it's the same thing. That's a joule. So the point is, the SI unit for energy is joules. So for power, energy per time, the unit is joules per second, which is defined as a watt. A what? Oh, a watt. A what? Sorry, I never get tired of that dumb Bill Nye the Science Guy joke. A what? A watt. A what? I'll see what broke later. Where have you heard watt before? Yeah, light bulbs. So you say something's 100 watts, or 100 watt equivalent. But anyway, for these fluorescent bulbs, that should now tell you that that's the rate at which it uses energy. And there's two ways to think of it. You can think of that as 100 joules in 1 second. Right? You're going to use 100 joules of energy in 1 second. You could, though, use a different amount of energy for a different amount of time and still have the same power, as long as the ratio is still 100 to 1. So you know what I mean? With power, let me just put it this way. You can do more energy in the same amount of time and have more power. More energy in the same amount of time. Or you can exert the same amount of energy, but in less time, it's the same power. It's all about the rate. Questions? Okay. So energy can be transferred and everything, but total energy is always conserved, and the rate we use as power. So again, running up and down the stairs, that's just, I increase the same height, it's the same amount of work. Let's calculate this one. I weighed this right before class, this block. Its mass is 712 grams. And I'm going to go, and it is 1 meter up. So its height is 1 meter. How much work did I do to lift it up onto that shelf? Figure it out. What do we do? Why do we want the weight? Yeah, we want a force, not just the mass. Okay, let's start with that. And that was mg. So, and we'll make life easy. Put this in kilograms as the standard unit. I'm at 0.7. I'll just round. Kilograms. Times gravity. We'll make that easy. 10 meters per second per second. So what do we get? 7 newtons. It's about 7 newtons of force to lift it, because that's its weight. So we have to exert a minimum of that up of 7 newtons. We'd have a net force of 0. It wouldn't be accelerating, but we can move it at constant velocity and get it up there. So we have to exert at least 7 newtons of force to get it up. Now what? There you go. How much distance? Work is force times distance. So if we take 7 newtons, how far did we move it? 1 meter. So we got 7 Newton meters, which is a joule. So how much work did I do to lift it up there? I exerted 7 joules of energy. Is that clear? Any steps in? Now with work, what if I do this? Okay, we start here, and I go, all right, how much work did I do from here to there? Oh, we got one vote for 0. Thought I heard somebody say 14. Why? 14 seems more obvious to me. So why are you saying 0? Well, you're right, and that's what I want to emphasize here. Is it has to do with distance, and we haven't moved it. Technically, there's a difference between distance and displacement. And technically, if you go on to another science class, this is displacement, and it hasn't been displaced. It's in the same spot. What's confusing is, yes, I had to exert some power. I used up energy to lift it up and down. Definitely. But in science, because it ended up in the same spot, we say no work was done on the block. Yes, I did work, but there was no work done on the block because it's in the same spot. Maybe a little more obvious is this. Push on the wall. Am I working? Yeah, we say I'm working. I'm expending energy, power. That took a certain amount of time. But have I done any work on the wall? No, it didn't move. I exerted a force on it. It felt a force, but it didn't move. So I did no work on the wall. Force times 0. Another thing about work is it's the direction it moves that you're pushing it. So if I push this straight that way, then it's my force times that distance. But what if I push on it at an angle? Let's say in that direction. That's a worse, not as good an example. Let's try this one. Oh, that won't move it. I know. This might be a little more clear. If I pull straight on this, I exert a force on it in that direction. And I moved it a meter, so we could figure out how much work I did on it. What if I pull on this at this angle? What would I do? I exerted a force on this. Do I use that force in that direction? Even though the block only moved horizontally. What? I would use it. Is that what you're going to say? You would use the horizontal component. So one lesson. With work, the distance it moves and the force have to be in the same direction that you use. This and this. So in that case, if I'm pulling with a force that way, and it only moved in the horizontal direction, then this is a case where you'd break this up into components. This force, well, so I like drawing some axes. There's my horizontal and vertical axes. And just to see, okay, how much of this is moving it that way? You drop that perpendicular. And so that's the horizontal component in the x direction. Likewise, you drop a perpendicular to the other axis, the y-axis, the vertical axis, and that's how much is in the y direction. So it's this amount of force that's actually trying to raise it off the ground. It's just not, that must not be more than its weight. So the net force is still down, doesn't lift up. And here's the horizontal force. So if you wanted to figure out the work done on this block, it would be that horizontal component based on how far it moves in the horizontal direction. The easiest is if you knew these angles, you use trigonometry. If it's a right angle and you knew one of these or two of these, you could use the Pythagorean theorem. Or actually with vectors, if we put this on a graph paper, you could equal amounts. 1, 2, 3, 4, 5. Let's call it 6. And you did the same thing over here. 1, 2. By scaling, because the length of these represent the magnitude, you could approximate it that way. I would give you something to figure it out. I'm not expecting you to have to figure it out with trigonometry in this course. For those that go on, not to scare you, but it's, oh, never mind. I'm not going to go there. So what I want you to know is these have to be in the same direction to do that work. So vertically, how much work am I doing on this? How far did it move vertically? None. So no work was done on it vertically. Even if I'm higher up. Yes, I'm exerting a force, but it's like pushing the wall. It's not making it move, so no work was done on it vertically. Horizontally, yes. But I'm exerting more force than I need to move it horizontally. Thus, now that you know physics, it's a lot easier if I get down here. I don't have to use as much force to overcome the friction. So likewise, a bowling ball. This was a question. Well, I'll leave it to you to put the pieces together. When you bowl, whoosh, there's friction on the bowling ball. Is any work done on the bowling ball vertically? No. Yeah, the lane supports the ball so it doesn't fall, but nothing's done vertically. If you push on something at right angles to something, it doesn't even move, does it? We could take this. It's like the hinge. If I push here, my force is that way, and the door moves that way a little bit. But what if I push on it straight into the hinge? It doesn't rotate. Things don't really move. Whereas if these are perpendicular to each other, perpendicular at right angles, then you'll never move it in that direction due to that force. And so there'd be no work done, because that doesn't make it move in that direction. All right, I think I'm beating a dead horse. You guys get it. And you can calculate this. Now I want to do this one again. Okay. How much potential energy does it have now relative to the table? Its weight? What about its weight? Is weight energy? Weight's a force. I heard 7 joules. How'd you come up with that? All right, let's do that. The formula. What form of energy does it have now? Potential, which is mgh. It's about 0.7 kilograms being accelerated at 10 meters per second, and it's 1 meter high, and you do all that, and you get 7 joules. So yeah, you can just plug it in. Now, did anybody realize the shortcut? Conservation of energy. How much work did I do originally to get it up there? We already found that. So how much energy should it have now? 7. It's conserved. If I knock it off now and let it fall, what form of energy will it have right here, right before it hits? Kinetic. Will it have any potential? Yeah, very, very, very small. It's going to 0. So right before it hits, we can say it has no potential energy. It's all kinetic. And how much kinetic will it have? You're right. Say it louder and confident. 7 joules. Isn't that fun? I do 7 joules to get it up here. It now has 7 joules. 7 joules. Total energy is conserved. It just changes forms. I did work to change it. Gravity does work on it, its weight, over this distance. So gravity does 7 joules of work on it and changes it to kinetic energy. Now, watch this one. How fast will it be going right before it hits the table? How many of you went, oh, I don't know. Well, the work is 1/2 mv squared, and we know that's 7 joules through conservation of energy. Total energy is conserved. We know the mass is 0.7 kilograms. So let's see. If we do that, multiply the 2 over to there, and you get 0.7 kilograms, the mass, times the velocity squared is 14 joules. Follow that step? Divide by 0.7 over here on both sides. 14 divided by 0.7, which is is you okay with that? And what's the square root of 20? I don't know either. Let's see, the square root of 16 is 4. Square root of 25 is 5. So, 4.5-ish meters per second. I think that's cool. 4.47? I'll round to 4.5. So yeah, just given its mass and how high up it is, you can know all that stuff from conservation of energy in the different forms. I like energy. Before, we could have done this. If you start up this high and the initial velocity is 0, you're being accelerated at 10 meters per second squared, and you fall this distance, you could have, back in pre-exam 1 days, figured out how fast it was going. You might not like it. But you could have. You had initial velocity, final velocity. The change in velocity was caused by the acceleration, which was based on how long it went. Well, I find conservation of energy much easier when you have to figure these things out. Let's, I'll end with some clicker questions. So, 5 or 10 minutes for that. So let's do a few demos and see how far I get. Other forms of energy. You know, when a ball squishes, you drop it. So I raise it up. It's got potential energy. You drop it. Right before it hits, it's kinetic. What form of energy is it in when it's in contact with the table? Somebody said elastic. You know about that. Does it have any potential right now? Gravitational potential energy relative to the table? No height, so nope. Is it moving when it's in contact with the table? At least relative to it? Not much. So it's not kinetic energy. Where'd the energy go? Because it does bounce back up, comes back to kinetic, and then into gravitational potential. So where's it at when it's in contact? It's stored in the ball. There's something called elastic potential energy. It's like a rubber band. You can store energy in a rubber band. And you guys know this because, let's see, right? You could store energy in it, and then, oh, just missed you, Peter. You weren't even looking. It was like right here. So you can store it elastically. It just changes forms. But the total energy is the same. That's what happens in a spring. This is essentially like a spring. Here's a fun one. This has a squishy tip on the end there. So I cut out these pieces of newspaper. And then you toss it up and let it land. So I'm going to do work on it. What forms of energy are going to happen? When I let go of it, what form is it in? Kinetic. Where's that kinetic going to go? Potential. Gravitational potential. And then it'll come back down. What's happening? Turn back into kinetic, losing that gravitational potential. And then when it hits the ground, I'm always surprised how loud it is. It turns into sound. Sound is a form of energy, actually. It pops it. It makes that fun pop sound. We'll learn about fluids and pressure more later. But we got to do it again. Wah, wah, wah. Yeah, that popped. First one was better. All right, how about this one? Have a volunteer. This is one where you're going to let go of it and then not move and let it swing back. Who wants to try? Okay, Glenn. All right, Mark, we're aimed at you, so don't let us hit you. Just be on the lookout, though. Stand up there. About where I was at. Put your hands on this side. Raise it up to like your right about here. Touching. All right, and the idea is you're not going to move. You'll just let go of it. And let's see what happens, shall we? Thanks, Glenn. Yeah, you can't help it. You got to flinch. Why did it not hit him, though? We started with potential energy. It turned into kinetic, and then potential, and thanks for not pushing it, Mark, and then back to kinetic. Now it's both, and then back to potential. To have hit you, what would have needed to happen? Yeah, more energy would have came, and that doesn't happen. You don't magically create more energy unless Mark had pushed it. But as you mentioned, yeah, there's friction up there and there's air resistance, which dissipates some of that energy. A lot of people like to say it was lost. Total energy is conserved. What's that? We're going to get to efficiency at the end of this chapter, yes. That energy was no longer in potential or kinetic. It got converted into heat from the frictional force doing work on this. So yeah, it never hits you unless you move or unintentionally. Some people do that. How about a roller coaster? I'm going to save that one. I'm going to save that one because we're going to work on that one a little longer. So I'll do this one. This is some ball chain I bought at the hardware store. It's just one continuous length. You now know what happens. Well, you knew this before physics class. I'm going to pull it out of the cup, and what happens to it? It starts to fall because Earth acts on it and accelerates it at 10 meters per second, and it'll accelerate and go down. But Glenn's probably seen this. Let me just do it. Whoop! When it gets snagged. Yeah, it kind of jumps up out of it first before it falls. Well, it starts falling and then it jumps out. And I love this demo now. This is my favorite way to explain it because we've just discussed momentum, inertia, and energy. And you can explain it 3 different ways. 1, well, it's moving. It has to get up out of the beaker before it can fall. So it's in motion. It has inertia. It has momentum. And you can't just turn on a dime. So even though the rest of it is falling, the weight of that is pulling on it to slow it down and then accelerate it back, that takes a moment. It can't happen instantaneously as soon as it whoop. So it gets pulled up a little bit because of this momentum. In terms of energy, though, it raises up. It has potential energy. It falls and converts to kinetic energy. And right before it hits the ground, all of this potential energy would be converted to kinetic energy. So it would be going faster and faster and faster until it hits the ground. Not that I expect you to realize it, but if you video it, the bottom does pick up speed, but then it kind of reaches a terminal velocity, not because of air resistance, but the remaining balls on it are tugging on it upwards. Gravity's pulling it down, so it actually doesn't fall any faster. It stays at a constant speed towards the end. So it's not gaining kinetic energy, right? It has kinetic energy, but it's not gaining because it's not picking up speed. The velocity's not increasing. But it's still falling and losing what energy? Potential. So we're not gaining kinetic, but we're losing potential. Where's that energy go? Boink. Up here. It gains potential up here. There's another way you can look at that. All right. Let's ask a few questions and see how you're doing. So as we're pulling all this up, remind you that you have a homework due Sunday night. It's just on Chapter 6. We're not quite done with Chapter 7. We have a little bit with simple machines and efficiency. We'll do Wednesday. No class Monday. It's a holiday. Have fun. And then we'll we'll start Chapter 10 Wednesday, next time we see you, with projectile motion. Not the orbits part, just the projectile motion. And we'll finish that next week, and then you can have a homework that Sunday on those two chapters. And then we'll start Chapter 35 on special relativity. But this Sunday is just on Chapter 6. All right. Let's give you a question. I like this energy stuff. It makes sense to me. It always kind of had. I hope it does to you. It's like nature's way of keeping balance. All this conservation of momentum and conservation of energy. Total energy. So if you're getting stumped, that's essentially this question with some different values. Do this one next Wednesday. See a few of you still calculating. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's less of you voting today. Maybe there's less of us here. All right. Mostly D, but some in A. The D's have it. What's the difference between A and D? A factor of 10. Is that helping anybody that chose A? What's that factor of 10 coming from? What do we know that's 10? The acceleration due to gravity. So if you just took the mass times the distance, that's not work. Work is the force times distance, and the force is its weight. So you have to take the mass times the acceleration due to gravity, which is 10. So 200 times 10 is 2,000. So it's 2,000 newtons. That's the force you need to do to lift it. Does that make sense? Does that help those that got A? And then so then that that 2,000 times the distance of 2 meters is the energy, 4,000 joules. So the 4 seconds, you don't need that with work. Work doesn't care about the time. But power does. Go. So it's the same thing. Just asking you about the power now. So you should know that it did 4,000 joules of work. You can start with that answer if that helps you. Oh, I got all snagged. Pause. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 2/3 of you say answer B. Correct. Power is the rate at which you use energy. So if you used 4,000 joules of energy, 4,000 in 4 seconds, 4,000 divided by 4 is 1,000. So yeah, it was 1,000 watts of power. Questions? We'll end on probably this one. We'll see. Go. Charging elephant, if it has kinetic energy, what else does it have? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. You got another response. All right. Momentum or all of them? Momentum. Let's start. Does it have work? That's things don't possess work. Work changes the energy they possess. Potential energy. Does it have potential energy? It could, but it didn't give you any reference. It's on ground. It's not like it's changing. It's not changing its height. So relative to the ground, it's on the ground. It has no gravitational potential energy to begin with. It's definitely not changing its potential energy there. So it must have, though, momentum, because momentum is velocity, mass times velocity. And kinetic energy is the energy associated with motion. So if something's moving, you know automatically it has momentum and kinetic energy. That's what this one's trying to teach you. All right, to close, to send you on your merry way this weekend, one more form of energy. Energy in your book. You guys reading it? A lot of the questions I asked, they give you the answers right in here. If listening to me doesn't let it all sink in, I totally understand that. That's why you have your good friend, the book. There's a lot of energy in here. You can store it like this. If I twist a rubber band and store energy in the rubber band, then I can release it, and it turns into kinetic energy and potential energy, and it's, it's just loads of fun. And I know it was a corny joke, but have a great weekend anyway. Sorry, Kara.